It is our honor and pleasure today to host Professor Catherine Fries for our CFA Colloquium. Professor Fries is the Jeff and Gail Kodosky Endowed Chair in Physics at the University of Texas at Austin and Professor of Physics at Stockholm University, and the George Ankelbeck Professor Emerita of Physics at the University of Michigan. Katie obtained her PhD at the University of Chicago with David Schramm, and after postdoctoral fellowships at Harvard University, at the Kavli Institute for Theoretical Physics, and at UC Santa Barbara, and as a presidential fellow at the University of California in Berkeley, she became an assistant professor at the MIT. Katie is, of course, an extremely influential scientist. She developed theories about dark matter and the earliest stage of the evolution of the universe that have been transformative for the field. For example, she was one of the first to propose ways to discover dark matter. And Fries was elected fellow of the American Physical Society in 2009, received a Science Foundation Fellowship in Theoretical Physics in 2012, and she's the winner of the 2019 William Field Prize, which is given annually by the APS to a researcher who has made outstanding contribution in physics. And finally, in 2020, she was elected by the National Academy of Sciences. So today she will be talking about dark matter in the universe. So please, Catherine, the floor is yours.
Thank you for this nice introduction, and it's very nice to see everybody in these strange times. So I always like to begin a colloquium by thinking about human beings going back to antiquity. Must have asked the same questions that we do. Where do we come from? Where are we going? What are we made of? What is out there looking out into the sky? What is it? And they had creation myths. As of 100 years ago, we had ours, starting with the brilliant work of Albert Einstein. Soon after, there was the idea of, well, there were a variety of proposals, one of them being the hot Big Bang model. And it is correct. I mean, that's just phenomenal in human history if you think about it. So the progress over the past 100 years since cosmology really started as a modern science has just been amazing, and how fun that we've been able to participate in this expansion of our knowledge about the universe all the way out to most of the observable universe, understanding the basics of what's going on. So, and a lot of this happened more or less at the turn of the millennium, answers to big questions. We know the geometry of the universe. We know the energy density of the universe, the age of the universe. But although we know so much of the physics, we don't know what the universe is made of. And so these are the big questions. What is the dark matter? What is the dark energy? That has been one of the things that I focused my research on. So how do we know? One of the major tools that we've used to learn about the universe has been the cosmic microwave background light that comes from 380,000 years after the Big Bang, which is nothing compared to the 14 billion years of age now. So this is light that you had photons interacting with electrons early on, so you couldn't see anything. But then at this time of 380,000 years, all of a sudden the photons are able to travel all the way to us. And looking backwards in time at this early light from the Big Bang, from right after the Big Bang, this is the Planck Space Telescope data, where the hot spots are temperatures slightly more than average, 1 part in 10 to the 5 bigger than average, whereas the blue spots are cooler than average. And it is from the size of these spots that we learn the geometry of the universe. So the prediction was that if the geometry of the universe is flat, light would move in straight lines, and then you should observe a lot of power at 1 degree angular scales. In other words, if the size of those hot spots is 1 degree in scale, that would be the case if the geometry of the universe is flat, and it is. So here's the Doppler peaks just sticking right out there. It's one of the great discoveries of human history, in my opinion. And then because of Einstein's relativity, which connects geometry of space-time with the mass and energy content of the universe, the implication is that we know the total mass and energy content of the universe to be 10 to the minus 29 gram per cubic centimeter. And by contrast, water on Earth is 1 gram per cubic centimeter. And if I had time, I would tell you the story about how I tried to explain when the Queen of Sweden asked me what is outer space. I decided that this is the definition of outer space, and I tried to explain it. Didn't work out very well, but it's a funny story that you can ask me later. So from the Planck satellite, not only do we know the geometry of the universe, but we also learn about the content. And so, for example, in here, we have the baryonic content, the ordinary matter content, as well as the cold dark matter content, and then the parameters of inflation. These are the 6 main parameters that are fit to those peaks, the 7 peaks in the data. And before I go on, I do want to I have to tell this joke, which is that in the earlier WMAP data, you have in here the initials of Stephen Hawking, and they're still there, of course. So one of the things that is still a puzzle is the extraction of how much dark matter and dark energy there is from these data. And this on the left is from WMAP, and this one on the right is from Planck. And you can see the numbers have changed a little bit. So the amount of baryonic matter in WMAP versus Planck it's around 5% of the universe. So everything that we're used to in our daily lives, 5% of the universe. And then from WMAP, it was 23% dark matter, the best fit, and in Planck it's 26%. And obviously there's only one answer. There's only one universe. There's only it's the same data that we're looking at. So this discrepancy needs to be at some point figured out. But for the moment, the thing I want to extract from this is that you've got 25% dark matter, 70% dark energy, and that is the bulk of the universe, and we don't know what it's made of. So these are big questions. The dark matter problem itself, which is what I'll focus on for today's talk, is it 90 years old at this point? Yeah, it's 90 years old. It dates back, actually, when I was in Sweden, I learned about the work of Knut Lundmark, who already noticed that that things are moving, the same kinds of thinking that Zwicky did a few years later. So, but the idea was so unpopular, they kicked him out of Sweden and moved him to Lund, which at the time not much was going on there. Somebody wanted to hear about it. But so back on Zwicky, he's a Swiss scientist working in the mountains above Pasadena, looking at galaxies in the Coma cluster, which has hundreds of galaxies, and noticing that they are moving too rapidly from the perspective of, based on the stellar, the light that he could see, you could predict how fast things should be moving, but these guys are moving too rapidly. So a proposed explanation would be dunkle materie, or dark matter, that is pulling on these galaxies and speeding them up. And with the word dark, it just means it's not stars, it doesn't shine. There was a lot of work after that, hinting, going in the same direction, but it was really the work of Vera Rubin and Kent Ford in the 70s that nailed this problem. They looked at galaxies and found evidence in every single one that dark matter is there, which led to scientific consensus that this is a problem, not just in one object, but it's everywhere, and we need to figure out what it is. Then the way that works, the rotation curves of galaxies is, if this is the center of a galaxy, and then you look farther outside at some radius r, some distance r from the center, and you watch things move around the center. Well, their velocities are determined by the amount of mass interior to that radius. And here's the equation, essentially the virial theorem, which is, here's the mass inside the radius, responsible for the velocity of the object. And so by watching the speeds, you can figure out what this profile is of the mass. And here's what the kind of thing that Ford and Rubin found. This is actually not from them, but it's the same idea. As you start at the center of the galaxy and you move out, then based on the stellar light, you would expect speeds to drop as you move farther out of things moving around the center, but they don't. The rotation curve remains flat. And as a consequence, if you add in additional material in a halo, then it adds up correctly, and you can explain these flat rotation curves. So our galaxy is, I wanted to use as an example. So this is the center of the galaxy, has supermassive black hole in there that weighs 4 million times as much as the sun, and were 2 out of the 3 people who got the Nobel Prize this year, Andrea Ghez and Reinhard Genzel, got it for the discovery of this supermassive black hole at the center of our galaxy. And we believe that every galaxy has one at the center. Now, moving out from that, you've got this pinwheel of structure, these spiral arms, and that's where the stars are located, including the sun along one of these. But if you take all this and you look at it sideways, that gives you the disk of the galaxy where the stars reside. And here we go again, is the sun 8 kiloparsecs away from the center. But that is only a small piece of the total. And instead, this is an artist's rendition of the Milky Way, where you have this giant spherical thing out here made of dark matter. So that was the original discovery of dark matter, was through rotation curves of galaxies. But since then, it's like a jigsaw puzzle with many, many pieces, and they all point towards the same thing. I've already mentioned the dark matter that has to be there for the cosmic microwave background, which is probably the strongest evidence of all, to be honest. But other ways to look for it, also Einstein's lensing. So when you have some dark matter here, made of whatever, doesn't matter what it is, although it doesn't give off light, it will bend the background light from some star and distort it, so that in fact what you would see would be something that's distorted, and you might see multiple images of the same thing. And by looking at these background objects, you could figure out how much dark matter is en route that lenses that background light. There's an app on your phone that you can use, created by a Michigan grad student, Eli Rykhoff, and you can have the correct equations lensing yourself if you want, more and more and more, which is what these students did. So here's some actual data from Hubble Space Telescope of some serious lensing going on. I don't know all the details, but you can see these sheared objects with multiple images of distant galaxies that have been lensed by the dark matter in the middle. And now you can do a computer reconstruction of the intervening material that caused that lensing. So I should caveat, this picture does not come from the same data as the previous one. I just picked the two best pictures, but this is exactly the same idea. Also from Hubble Space Telescope data, reconstructing the mass density. Well, you've got these peaks from galaxies, because this guy is a big cluster, and there's also dark matter in between the galaxies. So you've got galaxies containing dark matter, and then clusters having even more in addition to that. And the bullet cluster is a famous case showing that there really have to be two different types of mass. The idea here is that you have two clusters of galaxies merging with each other. And so far what's happened is there was a single collision of the two clusters. And when that happened, the atomic matter, shown in pink, and discovered because it's gas that gives off X-rays, the atomic matter gets stuck. It's as though you and I collide, and of course we don't go through each other, we get stuck. We have strong forces, we have electromagnetic forces that play a role in getting this gas to not move very far after during this collision. However, there you can see a clear differentiation from a second type of mass shown in blue, and again discovered by lensing. And so this stuff did not get stuck, it just kept going. Of course, it feels gravity and eventually will equilibrate and virialize, but on the first collision, it just kept going. So this is evidence for two types of matter. And so I've shown you a few of the pieces of evidence for the existence of dark matter out of the many that are there: rotation curves, gravitational lensing, bullet cluster, peaks in the cosmic microwave background. I haven't even talked about Big Bang nucleosynthesis, which is an older and very convincing story as well. So I also always like to show a picture like this, which is that because we would not be able to exist without dark matter, because ordinary matter wouldn't cluster quickly enough to allow galaxies to form. The reason being that ordinary matter talks to photons, which stream out of structure. On the other hand, dark matter can start clumping much earlier and produce the gravitational potential wells for large structures that the ordinary matter later falls into. So we're starting with initial conditions from inflationary cosmology, where instead of having the matter completely uniformly distributed, there are certain regions that have more matter in them than their neighbors, and those overdense regions pull in more matter, et cetera, and eventually form galaxies. So in this simulation, it's an old one by Andrei Kravtsov. In blue is shown, this is dark matter simulation only. So these blue dark matter particles are going to clump together, exhibiting more and more structure until you get to today in this simulation, where you have these long strands of structure with galaxies at the nodes of these filaments. And this simulation is a good match to the real world. So back on the pie chart of the universe, so dark matter is there in abundance, more of 5 times as much of it as ordinary matter. And the question, of course, is, well, what is it? And early ideas would have been hot gas or rocks or cool neutral hydrogen, but they were ruled out rather rapidly because of various observational consequences that they would have had. So before 2000, there were 2 camps: the believers in machos, the idea of massive compact halo objects, mostly probably made of baryonic material. And then the other people who were saying, no, this was, before it was clear how much dark matter there had to be, that it was, but so now we know that there must be something exotic going on. But anyway, so the believers in exotic candidates. And so on this subject, so I worked on both of these topics, and I want to say what are machos? Well, the possibilities would have been faint stars or substellar objects, because as you go to lower and lower masses, then there are more and more objects. And so it could have been there's just a ton, and that would explain the dark matter. Or it could be stellar remnants, white dwarfs, neutron stars, and black holes. And so on the theory side, let me back up. On the observational side, HST and some theory, a combination of that and theory, showed that these guys are only 3% of the universe, and the rest of this is only, white dwarfs could be on a 10% level or something like that. And so that was what we came on the side of theorists. And then you also had the microlensing experiments, and Charles Alcock was the leader of the macho experiment, which also showed that faint stars and all the way down to Earth mass, there's almost nothing there as far as explaining the dark matter. So it cannot be machos. Baryonic dark matter is not enough, which leads us to these exotic candidates. From the beginning and still to this day, there's 2 top candidates for dark matter, the WIMPs and Axions. And the reason for that is that they're not invented just to solve the dark matter problem. They're already there in particle theories anyway for other reasons. And so you're killing 2 birds with 1 stone. But before I get to those, I did want to mention some of these many, many very interesting suggestions for what the dark matter could be. Let's start with neutrinos. Wouldn't that be nice? They do exist, but it doesn't work. So in order for neutrinos to play in a mega neutrino is the fraction of the universe in the form of neutrinos. And so if neutrinos weighed 50 eV, then you'd have a mega neutrino equals 1. However, so you'd need something like that for neutrinos to play an important role. But we now know that the sum of neutrino masses adds to roughly 0.1 eV, which means they only contribute 0.5% of the mass of the universe. That's not going to fly. But that's relatively new information. But even already back in the 1980s, it was clear that neutrinos couldn't work because they're so light, they're nearly relativistic, and they stream out of structure. They destroy small scale structure. So that wasn't going to work. But I have been doing some work on neutrino mass because there's so much we can learn from cosmology. It's really amazing. So what is the status of our understanding of neutrino mass? Well, we know that there are now several observations that give us mass differences. So these are neutrino oscillations between the first and second lightest of the, actually, I shouldn't say that. I'll call them 1 and 2. There's a mass difference between these, and then a mass difference between these, where we know that the difference between 1 and 2, we know that from solar neutrinos, that you had neutrino oscillations from when they left the sun, electron type neutrinos, to when they got here, first seen by Ray Davis. And so this new one is primarily, it's a mass eigenstate made of a combination of the weak eigenstates, but it has a big chunk of nu E in it. The second one has a big chunk of nu mu, and the third one is nu tau. So we know these mass differences, but the weird thing is we don't know if nu 3 is the heaviest or the lightest. All we know is the mass differences. Okay, so this would be called the normal hierarchy, where the nu 3 is the heaviest, the one made mostly of tau, and this is the inverted hierarchy. And depending on which one it is, from oscillations experiments, well, the only thing we do know about the total sum of masses is that it's bigger than 0.06 in one case or bigger than 0.1 in the other case. So going after the hierarchy is, you can learn about it by learning about the sum of neutrino masses. Well, so from oscillations, we know mass differences, and that has led to several Nobel Prizes. Oh, I got to go to a really, really great party, let me tell you, in Sweden for the Nobel Prize a few years ago for neutrino mass. That was really very, very wonderful. But anyway, so these tiny neutrino masses are the only piece of physics we have beyond the standard model of particle physics. So on the theory side, it is a very important problem to work on. And the other question is, of course, what is the absolute scale of neutrino masses as opposed to just their mass differences? And there are many ways to look for this, including tritium beta decay, neutrinoless double beta decay. But what I wanted to talk to you about is the role cosmology can play. So it's basically a combination of CMB plus large scale structure data that bounds neutrino mass. So here we have the sum of neutrino masses that plays the role in cosmology that we're able to test, at least at this point. And the Hubble versus the Hubble constant, there's some degeneracy in the CMB. So the Planck data, for example, has this degeneracy. But if you add in BAO, a large scale structure, then this narrow window narrows, and we actually came up, we found this bound a few years ago. The sum of neutrino mass is less than 0.15 eV, and that was fun. It got into the Particle Data Group's review of particle properties, the book of properties of particles. Now from the Planck satellite has re-examined this and has a tighter bound 0.12. And reminding you from the oscillations greater than 0.06, cosmology is really narrowing this window. It's pretty cool. So what do neutrinos do to large scale structure? Well, they suppress small scale structure, actually. So the heavier neutrinos, they stream outer structure, and so they suppress the small scale structure. That's how you go after, that's one of the main ways you go after them. And everything I've said about neutrino mass from cosmology was assuming lambda CDM, but what if that's not right? Well, so we decided to look at that, and as long as you have any arbitrary dark energy, can be dynamical or constant, doesn't matter, as long as W, the equation of state, is always greater than or equal to -1, then actually, that's the interesting thing, is that in that case, the bounds actually get tighter. So these bounds from cosmology are really very strong. You have to, so pretty much any model of dark energy, you're going to maintain or even improve upon these bounds. So this also leads me to tell you about 2 microwave background experiments that I have joined, and the role and what we're going to get out of that. As far as neutrino mass. So the reason I joined initially was because I also work on inflation, and I want to know. So I have a model called natural inflation. I wanted to know, is that model right? And so the thing to go after is this parameter R, the tensor to scalar ratio, and this. So Simon's observatory is going to get very nice accuracy on R, and guess what? It's also going to get great accuracy on the sum of neutrino masses. So this is pretty good stuff. So back on the this picture, the Simon's observatory, I wanted to show you where it is. It is in Chile in the Atacama Desert. So blowing that up, and then you get something that looks like this. This is not it. This is previous experiments. And it is at 17,000 feet above sea level. And it is, it got delayed by COVID, but should be taking data in 2023. So it's exciting times. Originally funded by Jim Simons with, I think he's given $150 million at this point. The other experiment that I'm part of is Spider at the South, Spider balloon experiment at the South Pole. So my group is doing these, is participating in these experimental efforts. So in sum, to put it all together, from oscillations experiments, we know the lower bound on the sum of neutrino masses, and from cosmology, we're getting with this upper bound. So the answer is neutrino mass is about 0.1 EV. But and cosmology is going to get us even closer to accuracy there. It's pretty amazing. So I'm not going to talk about, but if you are interested in sterile neutrinos, light ones with masses less than keV, then these postdocs put together, well, a bunch of us, but put together the bounds, all the different bounds from cosmology and laboratory searches. So this is a compendium of all those works. So anyway, neutrinos can't be the dark matter, although there's a lot of interesting science going on in looking for them, learning about their properties using cosmology. Sterile neutrinos, they're interesting. They have no standard model interactions. It would be a fourth type species of neutrinos. And we were talking about that before the talk started, actually. Then primordial black holes. I think they're very interesting. And I wanted to have you look at a review written by Florian Kühnel, which was my former postdoc. So on the subject of primordial black holes, the reason they've gotten revived as being interesting is because LIGO has detected black holes, and it is possible that some of them might be made of primordial black holes, which would have formed in the early universe, for example, at phase transitions. And I'm probably trying to tell you too many things in one talk. I know I am going to run out of time, but I can't resist. So LIGO also found black holes that it shouldn't have, black holes in the mass gap. In other words, black holes between 50 and 140 solar masses should not exist because their precursor stars should have blown up as supernovae. So this is what they found. So the discovery of 66 and 85 solar mass black holes was a surprise. And so what we did was look at what happens if you put a new power source inside the stars, during their lifetimes. And then we found that you can prevent. So for example, a dark matter powered source, or it was we just left it arbitrary, and then you can prevent the supernova from the pair instability supernovae from happening. Okay, so moving on now to I mentioned at the beginning, I think the two best motivated candidates are the Axions and the WIMPs. And the reason is that they're already there in particle theories. And for example, I'm not going to talk much about Axions. They're very light particles, but non-relativistic. And they are automatically there in a proposed solution to a problem in the theory of strong interactions. And again, there's a review by a former postdoc of mine that is great, where the two relevant parameters from the experimental point of view are axion mass and axion coupling to photons. Now, the axion that solves the strong interaction problem is shown in these yellow curves. And you can see people are not just looking at that, they're looking all over the place at ALPS, axion-like particles, as potential dark matter candidates. And for the actual QCD axion, this ADMX experiment is going to be very interesting, taking data and interesting results in the next few years. But as I said, I want to switch to WIMPs, which is what I've worked on quite a bit. And these are weakly interacting massive particles. Billions pass through your body every second, 1 a day to 1 a month hits, depending on the exact details of the cross section. So as I was saying before, if dark matter does not have strong or electromagnetic forces, well, what else could it have? Well, okay, so it could have the fourth force in nature, it could have the weak force. And so if you make that postulate and then you have these things weigh between 1 and 10,000 GeV, then the reason that people got so interested is because you have they call it the WIMP miracle. It's a coincidence, I don't know. But anyway, with only that ingredient, you get the right WIMP abundance to explain the dark matter. So these particles annihilate among themselves in the early universe until the universe expands to the point where they don't see each other anymore. And this is what's left. So the fraction of the universe in the form of WIMPs turns out to be just dead on if the cross section for their annihilation was a weak interaction cross section. So that's why people got so excited about WIMPs, because you get the right answer with pretty normal physics, weak interactions. Now, the other thing that people got excited about is that there are particle theories with WIMPs in them anyhow. So for example, in supersymmetry, all the standard particles have partners, supersymmetric partners. And the heavier supersymmetric partners decay to ever lighter ones. And in the end, the lightest supersymmetric particle would be stable and could be the dark matter. So now the goal is, well, you've got a theoretically motivated candidate, can we find it? And so there's 3 ways traditionally to do that. It's the same Feynman diagram, but you can read it from left to right here in the 3 different cases. And there's also dark stars that I'm going to tell you about. So the first approach is to make them. So you take at the Large Hadron Collider at CERN, this 17-mile ring, then you have protons accelerated in opposing directions and allowed to collide at interaction regions where there are detectors. Just a few pictures. So this is one of the detectors useful for these supersymmetry and dark matter searches. One of them is Atlas, and this is Fabiola Gianotti, who was the spokesperson at the time of the Higgs searches, and she's now Director General at CERN. So we've all seen these giant pictures of this giant detector with somebody in front. And here we have the other interesting detector for what we're doing, the other general purpose detector, the CMS detector with Peter Higgs in front, where the LHC's big success is that they did discover the last missing piece of the standard model, this bump here, the 125 GeV Higgs boson. So if you ask people before the LHC turned on, for example, I asked David Gross what he thought the biggest goal of the LHC would be, and his answer was supersymmetry, supersymmetry, supersymmetry. And if you had two protons colliding, you could make supersymmetric particles, which decay in a chain until you get to the lightest one, the dark matter, which would escape detection. However, this has not been discovered at the LHC. Frustrating as hell. So now, you may have seen these plots, and I want to tell you the caveat to these plots from before I even discuss them, which is in order to, even the minimal supersymmetric standard model has 105 parameters, which obviously you can't plot. So if you make the simplifying assumption of the constrained minimal supersymmetric standard model, then you would have at a grand unified scale, a very high scale, you would have all the fermions have the same mass. And all the bosons have the same mass at this high scale, but that's no longer true. It would run with energy scale. But if you make that assumption, then there are only 5 free parameters, and you can make a plot like this. So old data, but the basic story hasn't changed. Nothing's been seen, which means you have to be up and to the right of these curves. In other words, the whole thing's pushed to higher mass. But again, that's with these assumptions that I was telling you about. And so we knew before the LHC turned on, if it sees nothing, can SUSY survive? Supersymmetry, does that rule out supersymmetry? And the answer is no. First of all, it could be at a higher scale. Second of all, these simple-minded assumptions that allow making these plots of fermion masses and boson masses being the same at a high scale, they may be wrong. And so you could even still have light dark matter around like 25 GeV or something that would still evade all the bounds. So it's a complicated problem. The other thing is, even if you find something there, well, it lasted long enough to escape the detector, but we want to find things that actually live the age of the universe to explain the dark matter. And so why not look for all these, if there's a billion going through your body every second, let's look for those that are living in the galaxy. Well, that is the idea of direct detection, where you have these WIMPs in the galaxy and they hit your detector, scatter elastically, depositing a small amount of energy, KeVs of energy, really tiny and difficult experiments with very low count rates, 1 count per kilogram per day, and look for that. So yeah, I do have to show this slide. How did I get into dark matter? Well, because my wonderful PhD advisor, David Schramm, got me into it. One of the founders of this field of particle astrophysics died flying his own plane at age 52. Anyway, graduate students, find a great mentor. I sure did. Anyway, so this takes me back to 1986, where I was a postdoc at CFA, and David Spergel was a graduate student at CFA, both of us with Bill Press. And I went to this conference in Jerusalem where I met Andre Druckier. And I ended up bringing him back to CFA to work with us, because Andre told me about work that he had been doing on elastic scattering as a coherent scattering of actual neutrinos with Leo Studolsky. And well, that's another weak interaction. So you can do the same thing with WIMPs, and Goodman and Witten applied the same problem to WIMPs, and it's actually easier to detect those because they're more massive than the neutrinos, so more energy deposit. And then we wrote the second paper on the subject, where we added a couple of things. So I did Feynman diagrams computing count rates, and David put in a Maxwell-Boltzmann distribution in the halo for what the WIMPs would be like. And we were making predictions for what these event weights would be. And so it's a The formula is basically number density times cross-section times velocity. And you can split it in this integral into the particle physics side of things, the cross-section and nuclear physics side, and over here, the astrophysics side, where this is the velocity of the WIMPs. And so we don't know exactly the scattering, and there's a variety of different possibilities. The one that I'm going to talk about more later is spin-independent cross-section scaling as atomic mass squared of the nucleus. And here's the simple Maxwellian distribution that we put in with the typical speeds of 270 kilometers per second. And guess what? It's still, from the detection point of view, this approximation works really well. So, and now to avoid cosmic rays, these detectors have to be in underground laboratories, such as this one, Snow Lab in Canada. And from the time that we proposed these things as an idea to what's going on now, well, this is the current status of worldwide experiments, even at looking for these things. And the only one that has seen any hint of detection is the DAMA Libra experiment in the Gran Sasso Tunnel outside of Rome. So I want to talk about that. So I'm moving too slowly. I'm never going to cover everything I want to cover. Well, so the idea here is that because the sun is moving around the center of the galaxy, it's as though we're moving into a wind of WIMPs. And it's like raindrops falling into your windshield. But because the Earth is moving around the sun, the relative velocity between us and this wind of WIMPs changes with the time of year. So we predicted that you should get a cosine modulation of the signal with a peak in June and a minimum in December. And sure enough, this is data from DAMA Libra, the red and blue dots, and that's exactly what they see. And now this is even more data, and it just goes on and on. I don't know how many, 13 years of data, 12 sigma detection. They are seeing an annual modulation. However, the question is, what is causing the annual modulation? So is it dark matter or is it something else? So the experimenters won't release their data, which makes people very nervous. And the other big issue is that other experiments don't see anything. Here's leaders of some of these other experiments, Juan Collier, commenting on the leaders of DAMA and Xenon. I'm a Spaniard caught between two Italian women. A lot of strong personalities in this business. So I was saying that in order to compare different experiments, well, it's apples and oranges because they're made of different material. So if you have the scaling, the cross section goes as a squared, it's been independent, then you can divide out the a squared and put everything on the same plot. So that's what has been done here. That assumption's been made, and there you have DAMA in green, where this is WIMP mass and this is strength of the interaction. So DAMA fits these two green regions, but the xenon-based experiments tell you you have to be below the red and green regions. So spin independent looks like it's not going to work. However, we don't know what the actual cross section is, so this is not good enough. This is just a more recent update of the same plot. And in the future, these experiments are getting bigger and bigger. You're having, right now, xenon is 1 ton. It's going to be up at n ton in size, and the experiments are just getting more and more accurate. There is right now, xenon does have an excess at the lower energies here at 2 to 3 keV. So this is events versus energy. They have an excess. And we thought about this, and a lot of people did. And the thing is that most new particle explanations just plain don't work. The only one with the right spectrum would be axions from the sun, okay, which is shown in purple here. But this interpretation is ruled out by stellar cooling of different types of stars. So it's what they're seeing is probably statistically going to go. It's just statistics. It'll probably go away, but it is sitting there. So just wanted to point that out. Now, the thing that really has to happen is other experiments that are made of the same material as DAMA, namely sodium iodide crystals, have to check and do this measurements. So then you can't worry about the apples versus oranges anymore. And so that is happening. So there's 3 experiments that are doing that, and I'm going to show you results from 2 of them. So cosine 100 is it's a Korean. It's in Korea. It's also a Yale involvement in other U.S. universities. And so this is DAMA Libra sitting here with their peak in June, because this is the phase of this of the annual modulation, and the cosine 100 1.7 years of data is not statistically able to say anything yet. Give it another few years, it can either confirm or rule it out. Last week we had new data from Anais, which is a Spanish experiment in the Canfranc laboratory. So again, this is modulation amplitude, and DAMA is sitting up here at 10% effect. Well, it looks like 1%. I'm a little confused about that. But anyway, so DAMA is sitting up here. And these guys only did an analysis in these rather large bins, 1 to 6 and 2 to 6 keV for the Anais, but they do not see the same modulation and their intention at 3 sigma. And so the joke people are making now is, well, cosine 100 will maybe come in the middle, and then we still don't know what's going on. Anyway, so the status of all of this is that finally there's detectors made of the same material. That's great. And on the theory side, well, we try to match the null results from xenon experiments with the potential results from the DAMA experiment, and using all different types of operators, different pieces of nuclear physics turns out are important. So it's a little complicated. And well, we'll find out what's going on, I think, based on these upcoming experimental results. So fun to think about going farther. In those pictures I showed you, eventually ordinary neutrinos are going to be in there as well. So how do you differentiate WIMPs from neutrinos? And a major step forward would be directional capability, if you knew the direction the WIMP came from. And so in that case, you would just point into the WIMP wind or point away from the WIMP wind, and that would already give you a factor of 10 difference in the amount of signal. So that would be a great thing to be able to do. And so here's some ideas we had for this. This again with Andre Druckier, David Spergel, and some very eminent biologists. So this, you can buy this from Illumina Inc. This is a nanometer thin plate of gold with DNA hanging down. And the whole idea for us would be that a WIMP would hit the gold, and then the gold would move down through these strands of DNA, breaking the DNA. But because of all the remarkable technology that we have with DNA, you can figure out where the break happened. You can control these strands, and you can look at the pieces that fell down and figure out, aha, that is the track taken by the gold, which is more or less the direction the WIMP came from. So WIMP is not breaking your DNA, but the gold would. So, and we're not going to use gold if we go to large sizes, but since this technology exists of binding the DNA to the gold, that's the place to start. So another idea we had was paleo detectors, which is, in lieu of using tons of xenon material, you could use small rocks from deep underground that have been collecting signals for a long time, namely 500 million years. So that was the idea. We call it paleo detectors. And the thing is that back in the day, people wanted to use mica to do this, but we can do much better now because these tracks are nanometer scale, like 10 nanometers in length. And so, and now there are nano tools that exist to identify what these tracks are doing in a way that you couldn't have before. And we took very carefully thought about uranium as the major contamination for that. Okay, so we talked about 2 ways to search for WIMPs, and the third one is indirect detection, where dark matter particles annihilate wherever there's a lot of them. So like at the center of the galaxy, there'd be a lot of dark matter particles, and the annihilation products in the end, after a chain of stuff, end up being neutrinos, gamma rays, and positrons that you can look for all 3. That's happening. So AMS found an excess of positrons that created a flurry of activity, but no way. So this is Douglas Adams, those of you who know him. Anyway, so AMS, to explain the AMS data, the cross-section versus mass would be here, but Fermi-Lat dwarfs tell you have to be below here, so it doesn't work. So the positron excess is very unlikely to be from dark matter. IceCube at the South Pole looking for neutrinos has not found signals of dark matter yet. Found other interesting neutrinos though. And then the third one is the Fermi satellite looking for gamma rays. And this is the gamma ray sky. So Doug Finkbeiner was the first to notice these giant bubbles here, these Fermi bubbles. And smack in the middle, there is a small region that's a spherical region that after you subtract everything off is still unexplained, and it could be due to dark matter annihilation into photons at the galactic center. However, it could also be pulsars, it could be point sources. It's a tricky game, and please do talk to your local people who are the experts on that. So in short, as where we stand now, well, we've got DAMA, we don't know what's going on there, and we've got this Fermi gamma ray excess from the galactic center. Those are still interesting things to watch out for. So now I get to talk about my baby, the dark stars, the idea that dark matter annihilation can power the first stars to form in the history of the universe. So this is work with me, Doug Spoliar, and Paolo Gondolo. We had this idea, and we didn't know there was already a movie, a cult film that predated us. And since then, we've worked on it with a lot of other people as well. And the basic idea is that the first stars form at a redshift of, I don't know, 20. The universe is a few 100 million years old. And they are made of, so, you know, I'm going to stress this over and over again. Dark stars are made almost entirely of hydrogen and helium. The dark matter is only 0.1% of the mass of the star, okay? So what happens in the early universe is that you get a collapsing cloud of hydrogen smack in the middle of a million solar mass halo of dark matter, a mini halo. And so smack in the middle there, you have a nice hot, fat, you have lots of dark matter. And as this gas cloud cools and collapses, it pulls in more dark matter. So normally it would keep collapsing until it made a protostar, but with the dark matter annihilation becoming significant, that is a heat source that can stabilize this collapsing thing while it is still bigger. And not only does it stabilize it against collapse, but it actually becomes a real star in hydrostatic and thermal equilibrium and so on and so forth. So I guess the missing piece that I forgot to say is that what happens is what does the dark matter annihilation do? Well, the products mostly get stuck inside the collapsing cloud of hydrogen once the hydrogen's dense enough. So the electrons, positrons, the photons, all of that ends up stuck inside the hydrogen cloud and heats it up. It thermalizes with it. So you end up with, sort of in my outline here, this is this additional phase of stellar evolution could last millions to billions of years, with the dark stars potentially growing large enough to be seen in the James Webb Space Telescope and to serve as precursors to the very early supermassive black holes once the dark matter runs out. So I'll show you here, this is an HR diagram of the dark stars when they first form are maybe 1 solar mass in size, but they're very weird. The mass is 1 solar mass, but the radius is 10 AU. Do I have these things written here anywhere? No. Okay. So they're big puffy objects, very cool. There's no fusion going on because it's not hot enough for fusion. And the surface temperature is maybe 10,000 Kelvin, which means it can continue to accrete. Normal stars can't because they have ionizing radiation coming up, but these things get bigger and bigger and bigger. And so we followed them depending on the WIMP mass and so on. So these are the ones I've been telling you about so far. So let's say with 100 GeV, this is just purely gravitationally being pulled in, the dark matter. This thing just keeps growing and getting brighter. And so we looked at this, and yes, they can be seen in the big ones. If they grow to, let's say, 10 to the 6 solar masses, can be seen in the James Webb Space Telescope. These are the filters, and yes, you stick out above the filters. And for example, here's a 1 million solar mass one that would be a H-band dropout, which tells you that it's roughly a redshift 12 object. So John Mather and John Gardner of the JDOST asked us to try to make estimates for what they would look like, how many there would be, and so on. So that's not easy, but you know, we did what we could with that, and we hope to find them. All right, well, what happens next? Well, eventually, once you run out of dark matter, then you're no longer stabilized against collapse. the heat source vanishes, and so you collapse and turn into, if it's small enough, a fusion powered star, or if it's large enough, it'll go directly to a black hole. So let's say you had a 1 million solar mass black hole at a high redshift. Well, that's very useful because you can merge these things together to make supermassive black holes that are seen, well, especially the high redshift ones are interesting, and the ones in centers of galaxies and as well. So very challenging to form a 10 billion solar mass black hole at a redshift of 6, okay? And so if we give you 1 million solar mass seeds, that's a great thing. Or here's another one, redshift 7.5 and 800 million solar mass black holes. So giving seeds for that is a good thing. So I talked about all these different ways of looking for WIMPs, the direct detection, indirect detection, collider searchers are looking for dark stars. Oh, dark stars don't have to be powered by WIMPs. We're now looking at self-interacting dark matter as well. So I only talked about part of the potential story, as we talked about before starting the colloquium. There are also unexplained lines, 3.5 keV X-ray lines. And then this is Randall Smith is the expert, and he tells me there's probably a better explanation. Oh, and I wanted to mention Fabio Pacucci, who is working on the supermassive black holes, or the explanation of the supermassive black holes. So I hope to have a chance to talk with him further about these things. There's also an unexplained line at 511 keV, which could be from MEV dark matter. So that's kind of the experimental status of what's going on. If I have a few minutes, I think I do. I'd like to talk about something entirely different, which is using Gaia data to test the nature of dark matter. So this is a European satellite that measures the positions and velocities of a billion stars in the Milky Way. And if you can see exactly where the stars are and how they're moving, that'll tell you about the gravitational potential of dark matter, so you can learn about the dark matter. Now, historically, this is the accuracy in the resolution in arc second, starting from Hipparchus all the way down to Gaia today. I just think that's historically quite interesting. And so one of the things that we are interested in is, when I say the nature of dark matter, is it cold dark matter? Is it self-interacting dark matter? Is it warm dark matter? And so one of the things that would be really nice to know is about the centers of galaxies, because in standard cold dark matter, you expect that this is the density as a function of radius out of the center of the galaxy. You expect a cusp. The dark matter goes up with roughly 1/r as you move in here. That's cold dark matter simulations alone, Navarro NFW profile. But of course, baryons are going to modify that. So later on, that could get flattened out because of supernovae or who knows what. But anyway, that's the cold dark matter prediction with dark matter only. Whereas a lot of times people look at galaxies and even the observations it's hard to tell, but sometimes they see cores instead of cusps. So does that mean there's baryonic physics that made the cusp turn into a core? Or does it mean we've got the wrong type of dark matter? Maybe it's self-interacting dark matter, which would give you a core. Although there's a recent paper last week by Mike Boyle and Cochin and Omid Someh, both at Texas, who showed that even with self-interacting dark matter, the baryons are going to recreate in like Milky Way sized galaxies. You're going to get a cusp back, which is going to make this distinction of which is the right answer more difficult. But anyway, so what we were doing was looking at streams in the Gaia data. So we know there's roughly 70 of them. And let me show you a picture. Okay, so here are the streams, the GD1 stream, the JLM stream. And my postdoc, Kayati Malahan, has a code that he calls Stream Finder, so to help find streams. But so what we wanted to do is study, well, there's two types of streams. Some of them form by tidal stripping of dwarf galaxies, such as the Sagittarius stream. We see that being shredded apart. But some of them are by tidal stripping of globular clusters of stars inside subhalos. Okay, so that's the thing we wanted to study, where globular clusters are dense old star clusters with a mass of about 10 to the 5 solar masses, physical sizes, few tens of parsecs, and they're living inside halos. So the kind of scenario we were envisaging is that these are simulations of a Milky Way type host galaxy with a subhalo that, let's say 10 to the 8 solar mass subhalo that's going to fall into the Milky Way. And you have this globular cluster that's moving around, orbiting around this subhalo, and it's being torn up already inside the subhalo, even before the subhalo merges with the host galaxy. And that's the origin of the stream, is this globular cluster that got torn up. So these are some simulations of this globular cluster being torn up and turned into a stream as time goes on. And so what we found is that depending on the subhalo that the globular cluster came from, you're going to end up with different looking streams. So if the subhalo had a cusp, if you had a cuspy subhalo, then the final globular cluster stream has a lot of structure. Okay, so it's wider dynamically and hotter, and it has all these different components. But if you had a chord subhalo to begin with, it's a narrower stream. Okay, so they look different. And this is, again, it's so far just in simulations. And so this shows this behavior that the width or the velocity dispersions are for the cuspy streams would be over here. And so then what we want to do next is go look at real streams and figure out, can we differentiate between, did they come from cuspy or chord subhalos? And so our tentative initial result actually has a preference for chord subhalos, but I'm not going to say that's way premature to say that. And then another thing you can look at is gaps in stellar streams as probes of dark matter. I'm running out of time, so I'm not going to talk about the details, but things move. So you have a stream, but then something moved through it. So one of the subhalos or the leftovers of this accreted subhalo can move through here. And if you find small evidence for passage of small subhalos, then that is consistent with cold dark matter and harder with the other types of dark matter. So that's another thing to look at. So there's many things that Gaia can help with testing the cold dark matter hypothesis. There's this cores versus cusps and gaps in streams, as I discussed, the shape of the halo, subhalos that pass through the Milky Way disk left residual oscillations that you can look for, and you can get better estimates of the low dark matter density, which of course is important for these direct detection experiments. And the answer is always around 0.3. It's not wild. It's I don't know, 0.2 to 0.5 or something. So to summarize what I've said in this talk, neutrino mass is about 0.1 eV, and we're close to knowing the answer in part using cosmology. Very powerful. As far as the WIMP searches, this DAMA business is very peculiar. Oh, I forgot to say, there is no alternate explanation that anybody has, no background that people can think of that could possibly explain what's being seen. That's very strange. But anyway, so it's being tested. And so we should know by other experiments with the same material. So we should know in a few years. Dark stars. The first stars could have been powered by dark matter heating rather than by fusion. And then there's new ways to test the nature of dark matter using the data from the Gaia satellite. So now I'm dead on finishing the right time, and I'm going to take an extra minute to tell a joke. I haven't said anything about the big beast, the 70% dark energy, about which we know very little. We do know that it seems that something, well, let me just say this, that ordinary matter and dark matter, they both have the name matter in them because they feel gravitational attraction, so things clump together. Dark energy is very weird. It seems to have the opposite behavior of it's causing the acceleration of the universe, so it's somehow some kind of repulsive type of behavior. And which means that galaxies are not just expanding apart, but accelerating apart from one another on the average. And that allows me to tell my joke. So here, the three of us at a panel at the World Science Festival in 2011, we're discussing dark matter. And these three guys, oh wait, I haven't been on full screen. I wasn't on full screen for the whole talk? Yeah, what an idiot. Anyway. So here, these three guys were talking about dark energy. And so I said, the one thing we actually do know to be true, dark matter is attractive while dark energy is repulsive. Oh, and I wrote a book for the public called The Cosmic Cocktail, 3 parts dark matter.
Thank you for this wonderful talk. And we have time for some questions.
Well, hi. So thank you for a very interesting, very full talk. I've got a question about the direct detections of WIMPs experiments, because they're getting better and better. The masses involved are getting higher and higher, and the upper bounds are getting lower and lower. Is
Oh,
there
so right, you're talking about like the xenon experiment and things
the
like that.
xenon
Right?
experiment, for
Yes.
instance? Yeah.
Yeah. Mhm.
This started out with the work that Bernard Satterley started decades ago, and now the state of the art, I believe, is the xenon experiment. At what point do these upper bounds become seriously embarrassing for elementary particle physics, or is there just plenty of room at the bottom for them to keep going?
Yeah, that's a good question. Let me go back. I do want to go back to that slide where I showed the future experiments. So let me see if I can share that. Okay, so yeah, yeah, this stuff is going to get built. Okay, so Xenon 1 ton is already taking data. I can't see where it is. Maybe this one. And so this stuff is going to happen. And this is competition from neutrinos. Okay, so this is solar neutrinos, and this is atmospheric and supernova neutrinos. So you're going to have neutrino detectors pretty soon. So, however, on the experimental side, can you keep going? And the answer is yes, because the spectrum will be different for neutrinos versus WIMPs. Because if you get directionality, then you're going to, if you found WIMPs, you'd learn even about the dark matter, where it is in the galaxy, and so on. Would that be great? So there's different ways to keep going anyhow. But obviously, it gets frustrating that we haven't seen anything, and it gets weird. So when do you stop? That's a good question. Are there theories down here? Yes. When we first did our calculations, I think about this sometimes. You know, we picked the simplest things. We picked Dirac neutrinos with Z mediated by Z's, you know, and photinos. They were like the simplest analogs of standard model stuff that we thought of. And when we did those calculations, you know what our predictions were? Up here somewhere. And if we had by chance picked something down here, nobody would have started building experiments, right? So that's quite a thought. So now so generically speaking, the simplest Z mediation stuff got ruled out right away. Now there's Higgs mediated, there's sort of major channels that start to get ruled out, and then it gets more difficult. But people are going to keep doing it, because I guess the original motivation is still there, and they know how. It's not that hard to keep going, you know. So, but from my point of view, oh, you know, when I first heard about DAMA, they had 3 days of data in the winter and a month in the summer. I thought, this is ridiculous. And I still, everybody's been so suspicious because they won't let us see the data, and I didn't know what to think. But you know, when I got excited, when I heard Frank Kellerprice, who's at Princeton, and he's made a living off of T violation experiments. I mean, he's Mr. Precision. And he says, you know, we have to go test this. And I thought, oh my God, you've got a careful experimentalist who's now going to devote himself to look for this. This is really serious. There really is no other explanation. I mean, and Xenon is sitting in the same lab right next to DAMA. So if there's some junk in the atmosphere, why isn't Xenon seeing it? This is a very, very peculiar situation. So in fact, if DAMA gets ruled out, we will never know what it was.
Okay, thank you.
That was a long answer.
Okay, but thank you.
Yes. So I have a question, actually. I was very interested by the description of the dark stars, of course. And
oh, good.
I was, yes. And you mentioned that the JWST should be able to observe them. So I was wondering what would be a smoking gun for a dark star as opposed to POP3 stars or more evolved stars?
Okay, so standard POP3 stars are less massive than 100 solar masses. And they stop, because they're fusion powered, the surface gets hot, so they can no longer accrete. They have ionizing radiation coming off. So that's the key difference, that they stop at 100 solar masses and they're not very bright. James Webb cannot see them. Okay. You can see an entire galaxy, but it cannot see an individual star unless it's a dark star, which is why they like us. Okay. Because we're giving them a target. And so what we're predicting is a very bright object. It could be 10 to the 10 solar luminosities, but still very cool, tens of thousands of degrees at the surface. Okay, so that's an interesting combination. Now, let me tell you what else we were trying to do. We were trying to see if they pulsate. And in order to, so the first code we wrote was very simple Mathematica, and basically got the right answers in a very primitive sense, but not bad. Then we used Peter Bodenheimer's stellar evolution code. It's an old Fortran 77 code from I don't know when, and we put in the new heat source there. Now we're using the MESA code, which is, those of you who are using it, that's a big deal, okay? That's a big beast, and modifying it is non-trivial, but we've done it. So we've managed to look at pulsations in a particular, for 100 GeV with a particular accretion rate and and so they pulsate until they reach 200 solar masses, and then they no longer pulsate, which is the opposite of what you want from an observational point of view. However, we have to explore the more general parameters space to see if we got that would be really nice, you know?
Yeah.
So what we have so far is big and bright and yet cool. And in the color magnitude, it's also got a particular location, you know? So in the meantime, I see Erwin here. Erwin, you asked me a question that I never answered.
That's true.
I know. You know why? Because it's a non-trivial question. So should I try to answer it while we're waiting here?
It's all right with me. Since
oh boy! So he wanted to know why. What does it take to get a flat rotation curve, basically? So I mean, if you start with the spherical cow, the isothermal sphere, with density 1/r², and you just have gravity. You have an isothermal equation of state, gravity, hydrostatic equilibrium, then it all works beautifully. Okay, so that would be great. However, why is it that NFW, these NFW profiles, which are 1/r in the middle and 1/r³ at the outside? So how that how this works to give you the flat rotation curves far outside the stellar disk, I don't know, to be honest. Does anybody, but we have an audience now who has a chance of giving a better answer to why are there flat rotation curves, not just in the spherical cow of the isothermal sphere, but more generally once you do these simulations.
Why are they always flat rotation curves? Why should the conditions be the same?
But in the meantime, we have the question from Joanna. So Joanna was asking online, there was a mention that DAMA could be explained by their annual noise reset. Is that a possibility still on the table?
Okay, so I'll be honest with you. I don't know what an annual noise reset is, but apparently no. I'm serious. I mean, there were, when they first came out with this result, people said, oh, it's radon, it's muons, it's it's all these different things. And then, you know, they are actually very good experimentalists on this experiment, and they went and tested every single one of these things and persuaded the rest of the world, no, it's not any of these things. So I haven't heard this one, but I'm going to say no. I'm not an experimentalist.
Thank you.
But it's
Thanks.
just, you know, if this were an actual resolution, well, I'm just going to say no, because one after the next, they actually have checked everything.
So I don't see any other questions. So let's thank our speaker again for a wonderful talk. And we will see you again next week for the CFA
It's so nice for me to see you all.